All right, we are now recording. Let's get the power. Whoops, that's not what I wanted to do. Pulled up to the right slide. Current slide. Okay. And maybe even turn on the projector. I mean, I feel generous today. But the system is terribly slow. Incredibly slow. Here we go. Now we get out of this, so show better. All right, is that going to come up? We'll see. Now, since it's your first time here, you've been in other classes though, so you know on Blackboard, under content, for this class, under content, you'll find the syllabus for the class. You'll find the research paper instructions for the class, just like the research paper instructions for both of your other two classes. You got a lot of research papers to write. Get going, okay. And some of the others too, okay. My locator card showing when I'm in class, out of class, in office, out of office, which campus I'm on, that kind of stuff. Then all the PowerPoints for this this course, actually more than we need, except one chapter. It seems like it's 14 is too big for it to load on Blackboard, and this sort of it's on their DVD. They don't let you mess with it, so I haven't been able to split it into smaller files. So when you get there, you just won't have that. Okay. Then, after that, I put out there a few, I can't remember how many, visual calculus, I know it was one, it seems like there's one or two other websites that either I found or students have found and given to me that said they found them useful for the course. You may or may not find them useful, but you can look at those. And then finally, the last, I think it's the last thing under content, you scroll way down to get there. When you finally get there, it's Math 227 videos or YouTube videos or something like that, and then you can catch up and see every class we've done in here up until then, and Matt's here. All right, so you can catch up if there's anything you need to catch up. Now, a little bit about what we were doing. I did teach 126 this summer, and we lost a week of class because of holidays. Memorial Day was one Monday, and 4th of July was another Monday, so basically we had a shortened term, so we didn't get as far as we needed to get. So we started here in chapter 11, wasn't it? Okay, 11.1, and we covered 11.1, 11.2, and 11.3, but 11.3 I think was just slideshow. Second? Yeah. So that was just a slideshow, not responsible for that. 11.1, 11.2 would be to some extent. 11.4 is still slideshow because this is polar area and arc length of polar coordinates. I haven't read the topic, the section topic clear, carefully. We ran out of time the last time. This again will just be a slideshow, but 11.5 conic sections will be useful for you later, okay? So we will go over 5, but that only gives us 3 sections in chapter 11. Normally, I only test on the first 2, but I combine that with another chapter. So let's just not have a test at the end of 11.5, but continue and get enough covered in 12 and combine 11 and 12 together and make a test out of that. Okay? And we'll need to get moving on it. So let's, again, just slideshow on 11.4, and here it is. And Cameron found this that I can use these little, you may not have seen them, or you may have. I can't show them to you now, but I'll try to point them out. They do have some little icons or something down there that are sort of hidden. And if I bring the cursor close enough to them, they show up well enough, I can do that. Okay, again, you're not going to be tested on this, but just in case you ever need it. What we're dealing with is area and arc length in polar coordinates. All right. So here we have a problem. R is some function of theta. We think of y as a function of x. This is r as a function of theta. Now, they set it up on xy coordinates. Don't worry about these xy coordinates. They're not entering the problem at all. Okay? It's the r and theta that are entering the problem, and they are the problem. So this r as a function of theta is this curve right here. We're interested in determining the area in this region under that curve. Okay? Now, don't know why they set it up the way they did, but it's perfectly fine to do so. We're going interested in the region from theta equal alpha to theta equal beta. So it's this region right here. Now, here's the part that's sort of strange. Why did they put the xy axis here? Why didn't they scoot it over just a little bit so the origin was right there? It doesn't matter the xy, where that is at all. It's immaterial to the problem, so you can scoot your own origin over to there. That's where we're starting from, and now that's how you measure alpha, that's how you measure beta. So now that problem makes sense. We just don't know what this function is, but whatever it is, if you're interested in that, that is the integral from alpha to beta of whatever function that is. Okay? Now, that's giving it to you sort of directly, glossing it over some. Here's what you're actually doing sort of in your, remember before we divide the x into partitions and then do x, y, that type of stuff. Now we're dividing the thetas into partitions, and you're finding the area of one wedge at a time, okay? Now, the area bounded by this curve, r is equal to alpha theta, r is equal to alpha theta, same curve there, and the two rays, theta equal alpha and theta equal b, you first divide the region into narrow sectors. Then, I think it's, at this point, it's just about as easy to do this, okay? And let's see, in the glare here, but this is, Jonathan, right? No. That's gracious. Tony.
Yes, sir.
Yeah, okay. I looked for that before. I thought I saw a P by the name. I thought, okay. All right. Now, they go back to a different looking picture here. But now this appears to be a circle, okay? A quarter of a circle. The area of a circular sector, so it is a circle, circular sector, is exactly 1/2 d theta r squared. 1/2 r squared d theta, delta theta. Okay? I don't know if you remember from your trig class, if this was just some angle theta here, it would be 1/2 r squared theta, or 1/2 theta r squared, however you wanted to refer to it. But now it's not a full theta, it's a delta theta, that little section there. So going back to the previous slide, that's how we would define the area of that. Now, if you find that a little hard to remember or rationalize or think about, you may not find this helpful, but to me it makes a little bit of sense. Just kind of imagine this is rotated down to there, so we're just dealing with that first little segment there, okay? Exactly the same area, it's a circle, you're just rotating that sector down there, okay? Well, that almost looks like a little triangle, doesn't it? And what's the area of a triangle, 1/2 the base times the height. Well, the base is r, and the height is close to being r theta. Okay, if you think of second, yeah, delta theta, but yeah, let's just call that theta. Then that would be r theta. So 1/2 r squared theta, but that theta we're now calling delta theta. So that, yeah, that's how you can think of it. Pull it up here and do the same thing here. Base times height. The height is r theta, so 1 r delta theta, 1/2 r squared delta theta. If that's helpful to you, it may not be. Well, going back to the previous thing, then we can calculate our, and here we have gone back there. Okay. And you're going from a theta j sub I minus 1 to a theta j. So this is your delta theta there. Okay. Your r, now this isn't a semicircle anymore, but as long as this is a pretty small theta, and this is a continuous function here, the r sub j sub minus 1 and r sub j are about the same. Okay? Especially if you get a smaller and smaller delta theta, they're almost exactly the same. And make it a d theta, and you can basically say they are the same. So the area of the j sector is approximately 1/2 r sub j delta theta, r sub j squared delta theta. Just like we had before, only let that delta theta, or that's what we're going to do, go to a d theta, and you've got it. Okay? So, what is our area of that entire region then? It would be counting the j's from 1 to n, if you broke that sector, the part you're trying to take the areas of, into n partitions of your theta. So j equal 1 to n, 1/2 r sub j squared delta theta. You're summing all those up, adding them together. The rj's may be changing length, that's fine. The 1/2 can come outside, and that would be, now, remember what r was? Alpha theta. So 1/2 alpha squared theta delta theta, going from 1 to n. Do a limit on that as your delta thetas go to a d theta, then that would be the summation from 1 to n. How many ever, initial to final. I think that was theta A to theta B, I think is how they said it. And sure enough, this is your area in polar coordinates. Probably saying too much about it since it's not responsible for it, but you might need it. I don't know what your individual areas are, but you might run into this sometime. This is how you do area in polar coordinates. If alpha theta is a continuous function, needs to be alpha continuous function of the angle theta, then the area bounded by the curve, by a curve in polar coordinates, and here's the thing, you have to be able to write that, that curve as r is equal to that function of theta. And the rays, theta equal alpha to theta equal beta, wherever those are, with theta being less than, alpha being less than beta, then your area between those is 1/2 the alpha to beta r squared theta. Okay? 1/2 alpha to beta f squared. And again, I like always to write the squared by the function, f squared theta d theta. I don't think you'll ever confuse that with alpha theta squared, but why risk it, you know, do f squared? That, to me, it makes more sense. All right, any questions? Okay. Now, next little bit here. This one is referring to one specific problem, example 1. I think we'd have to do the example since you're not responsible for it. I think I'm going to skip that one. Here's the picture for it. So if you do want to work those, there you can look at that. Here's the first. I'm sorry, I can hardly talk. I don't know why. Here's the first part of example 2, though. And again, this is specific for the problem at hand, so I kind of think, let's just go on over that one. They're talking about some other issues here. That's really problem example 2, and so I don't know why they did the other. But this just shows you sort of how, in a sense, complicated maybe some of the polar coordinate problems can look. And then figuring out what your limits are. This would be starting at theta 0 here. This is theta going to pi 6 and coming back around to pi thirds. So if you're interested in that area, your area swept is theta equals 0 to theta equals pi thirds. Okay? If you were doing the whole thing, you can do a variety of things here. But that's going to be a rose with 3 petals. You can just do 1 and multiply it by 3 if you're interested in the whole area. Notice here, it really doesn't make a lot of sense to, let's see, I want to say even talk about theta from pi thirds to 2/3 pi, but that actually tracks this part of it, and then that part, and then it just repeats itself. So this is only basically defined for thetas between 0 and pi. But you don't need to worry about that now. We're not doing the problem, so let's just move on. Just illustration of, they can get sort of bizarre and you have to really think your way through them. So take your time with them if you ever do. Now we're going to look at area between 2 curves. If you had one r as a function of theta, and a second r as a function of theta, and you're looking just for the area between those two, and this could get really strange drawing this, because it's strange enough drawing polar coordinates. But it's exactly as you would expect. 1/2 the first one squared d theta minus 1/2 the second squared d theta. The integral of the difference of 2 integrals is the integral of their difference, as long as they've got the same limits, and these did. Okay. Here's a pictorial representation of such a curve that you might be interested in. And again, why they put the XY axis in there anyway, you're not using it, but since they did, use it over here, I guess just to make it more you, I don't know. But if you're looking from alpha to beta, the difference between this F2 of theta, the F1 of theta. Now, I don't know if you remember, back when we did this in rectangular coordinates, we required the F2 always be greater than or equal to F1 for a given theta. And it looks like that's going to be the same requirement here. You don't want this one doing this and that one doing that. Your areas, you'd have to split it into 3 different multiple intervals of theta to look at separately. Okay, so that's just area between 2 graphs, how that would look. Okay, now again, this is, I think, referencing example 3. I don't think you really need, well, for some reason that didn't take. Okay, there we go. Okay. This region 1 here, this part here, is the difference between this, okay, several kind of weird things about here. You would need to know the limits of integration here. The two functions, this being a function, that being a function. And you notice that it's only going to be talked about between these two angles here. So minus 5/3 and 5/3. So you do that for the first function, r is equal to 2 cosine theta. And that's this one. But you only do it from minus 5/3 to 5/3. Subtract from that the blue circle, which is the, it's r is equal to 1. There it is. R is equal to 1. Subtract that. But again, only go from minus 2/3 to 2/3. You might say, well, couldn't you just do this one minus that one? Okay? Not quite. That would give you this area here that you really aren't interested in. You're just interested there. So again, unfortunately, you almost have to draw your graphs. And most graphing calculators will do polar coordinates, but I think you have to do some manipulation to make it happen. Okay, so learn your calculator. Oh, and Victor snuck in when I wasn't looking at it. I gotta watch him, you know. There we go. Good deal. Anyone else sneak in? Okay, got it. So again, we're not doing this, you're not responsible for it, but in case you ever need it, here's how you approach. And this is how what we just were looking at, graphically, this is what it comes down to algebraically. The area of the thing you're looking for is area 2 minus area 3, and it's pretty straightforward there, I think. But not doing the example, so going on past that. Now, first part was area between two curves. Second part was arc length. And there's a part of you that may think, shoot, arc length in polar coordinates should be quite a bit easier than it was in rectangular coordinates, and I'm not going to say that it is or isn't. It looks awfully close to the same to me. If you're looking for arc length in polar coordinates, you're going from theta equal alpha to theta equal beta, and I think this looks very close to basically what we had before. Square root of f squared minus plus a prime squared. I don't think it's the same thing, but it's not too far distant from that. Okay? There is a lot of lead on to that, about a paragraph or so. They're just giving you the summary here. That's what it turns out being. If you need it, there it is. Okay? And let's see, that's probably, no, one more slide here. This deals with example 4. So we're not doing it, so let's just skip on by that. Now, this is part of the summary. That was a slide we saw much earlier, basically the same thing, defining the area under a curve in polar coordinates, difference between two curves, okay, in polar coordinates, and that's it. So, not responsible for 11.4, but we will there if you need it. Now, what I do want to hit is 5. And I'm not going to take you into gory detail on that either, but there is a reason I want to go over section 5, conic sections. Usually don't cover this at all, just move right into, actually we should be in chapter 12 already, we're not, so that's why I'm trying to do this fast. And why is this not, okay, oh there it comes. I thought it was, let me click it again. I don't know why I've got that crosshairs. There we go. No. can't get it to open. What, this? Well, it says it is, but there's nothing showing. It just takes me back to that. What I think I'll do is go back one. There's something that my cursor is jittering like it's nervous or something. It's not responding to anything, it looks like. I may have to shut it down and bring it back up. Ha! I don't know what it did, but it did it finally. All right, let's get the slideshow from this slide then. Have y'all run into conic sections before? Okay. Let me first get rid of this. And then do that. Okay. What do we mean by conic section? What does the word conic means? Yes, referring to a cone, okay? And, you know, generally I don't spend a lot of time thinking about cones, but it's just sort of an interesting characteristic that you can refer to just about any of our analytical geometry shapes by a cone. Now, a cone, we usually think of half of a cone. Really, a cone is both halves sharing the vertex, okay, top and bottom. Okay, the various shapes that we have here, why they started the way they did, but if you do a plane that cuts perpendicular to the axis of the cone, and these have to be right circular cones, by the way. If you have that, then of course that's going to give you a circle, various radii, okay? If you take a plane and tilt it through the edge of one of the cones, it doesn't matter where, you're going to get a parabola, which is another one of our basic shapes. If you take that tilted plane, but make sure you cut completely across a parabola, not parallel or perpendicular to the axis, but at some angle to the axis, but that you cut completely across the cone, that gives you an ellipse, okay? And finally, if you take a plane that's parallel to the axis, but not on the, well, actually one on the axis would work, no, off the axis, then you get purple.
If it was on the axis, it'd be like absolute value type stuff.
Yeah, you would have the across, it would just go negative as well, because it would be bottom. So just off the parallel, in any dimension, but parallel off the axis, you get a purple, okay? A pair of hyperbola, I guess you would say. So those are our conic sections. Now, that's why we call them conic sections. Let me, okay, I don't want to get in super lot of detail here, but this is basically your definition for an ellipse, okay? Don't sweat it. You don't need to know this for sure, but an ellipse has two foci, okay? That's plural for two focuses, okay? Foci, F1 and F2. And basically, if the, kind of think of it this way. Put your two foci down, okay, and have a string that's longer than twice the distance between the two, and take a pen and run it around that, you're going to draw out an ellipse. So the PF1 plus PF2, this is your, any old point is equal to some constant length of the string. That gives you an ellipse, okay? Now, Skip a bunch of terminology here, but I'm going to throw it back in where I see it's appropriate. This is your generic fundamental equation for an ellipse. Okay? X over A squared plus X over B squared is equal to 1. That should be a Y. I was going to say, why do they have an X in there? What are they trying to say? They just messed it up. Okay, let me get my pen. No. Oh, yeah. Let me get my
You can change the color in.
Yeah, I know. Hey, my other one, I couldn't do this because it was in my slideshow. This one I can't. So, wait.
Yeah, and you can do all that.
Yeah. This is Y squared, not X squared. Okay. That's your general generic form for an ellipse. Okay. Now, let me go back and pick up a few things they skipped here. The midpoint between the two foci, that's the center. The ellipse doesn't go through the center, neither of the foci are on the center. What if the foci were on the center? You now have a circle. Okay. If they're not on the circle, then it's an ellipse, and the center is neither a focus nor is it on the ellipse. Okay? Now, depending on which is the larger number, A or B, the larger one's called the major axis and the smaller one's called the minor axis. The line through the foci is the focal axis, and that's usually the major axis. That is the major axis. Okay? Then they talk about the center line through the center perpendicular to that is the conjugate axis, which I was calling the minor axis, or, they call it semi-major and semi-minor because they're doing the distance from the center to that, so it's not the whole. So anyway, that's where the additional thing you need to know there. Okay. Now let's see. This is basically that first description I gave to you. You add the, this is from any point from one axis, from focus to that same point to the other focus. And by the way, this will be, let's assume your major axis is your x-axis here. Then your one focus will be C units to the right of the center, one will be C units to the left of the center. So this would be, but the Y is always the same. This is just your distance formula. Distance formula, that's equal to 2A. That's what they were calling what before, C or K or something. K. That's the double length of your string, basically. Okay, your major axis. Okay, twice the major axis. Okay. What's that?
K for German constant.
Yes, I guess so. Now let's see. Can we get all this on? I don't think so. But I think we can get enough to get it to show. Almost. Chops a little bit, but not too much. All right. The ellipse consists of all the points P that are the sum of the distance between that point P, any one of those points P, between one focus and the other focus. That sum is always the same. Okay? German K. Okay. Now, play around with that and you get, and by the way, the other things, This being the major axis, the conjugate, or the minor axis. I'm always used to hearing it called minor axis. They call it conjugate axis, which is fine. There's nothing wrong with that. And half of the major axis from the center to the long part of the egg there, that's your semi-major axis, and now they're calling it minor, from the center to the flat part of the egg, that is your semi-minor axis. Okay. So there's a formula. The important thing is this. That's the equation for an ellipse. Okay. Two-dimensional equation. Now they got the y in there correctly. Now, how does that differ from a circle? Your a's and b's are the same. So that would be x squared over a squared plus y squared over a squared is equal to 1. Which would then be 2x squared, x multiply both sides of a squared, you get x squared plus y squared is equal to a squared. What do we call the a then, if that's a circle? The radius of the circle. Just like that's a semi-major axis, semi-minor axis. They're the same. That'll be the radius of the circle. Okay. So ellipse or circle. Main thing to remember, you can write them both in the same form. For ellipse, x over major, semi-major length squared plus y over semi-major, semi-minor length squared. Unless, of course, the egg was shaped like this, and then this would be major, that would be minor. It doesn't really matter. But that's equal to 1. Exactly the same for a circle. X squared over r squared plus y squared over r squared is equal to 1. X squared plus y squared is equal to 1. Okay. Hang on to those. We'll use them later. Okay. Now, where are they doing? What are they doing here? I don't even see this in the book. I know it's in here somewhere. Oh, I'm sorry. Yeah, it's at bottom of the page, bottom of page 510. See. Oh, okay, got it. Yeah, bottom of page 610. Okay. So don't worry about this too much. It's basically telling how you got there. Now, this is the one I thought we had already done. Okay. All right, and by the way, I should have told you this sooner. My normal office hours on Mondays and Wednesdays are from this class is over with basically at 2 o'clock until 4:45. But most days I'm here until at least 5:15. Not today. Today I've got to go to the Birmingham campus. I'll leave here at 4:45 when I'm supposed to be getting off. I'm going to the Birmingham campus. The guy who called me and made me late getting or almost made me late getting class, I need to be him there at Birmingham campus. So that's, I won't be hanging around anything past 4:45 today. I can't. So here's theorem 1, ellipse in standard position. Now what do we mean by standard position? The center at the origin of your rectangular coordinate system. Okay? Also, which of course you have to have, A, which is usually considered the semi-major, has to be positive. B, semi-minor, has to be positive. So both of them are greater than 0, and this says A is greater than B, so that's what makes it the major. They introduce a C here, which basically is 2C is going to be the sum of that K that we had before. Okay. So ellipse, which is this, that's the A. 2A is a C. With one focus at, C is the focus, I said. C is at C0 and the other is minus C0. That's why they introduced the C there. Okay. That's your equation. Furthermore, the ellipse has a semi-major axis A, semi-minor axis B. That's if the foci are on the x-axis. Okay. Focal vertices plus or minus A0, minor vertices plus or minus B0. Okay. That's where they cross the x-axis and y-axis. Okay. Now, if, however, B is greater than A, if both are greater than 0, then you define it with the egg is along the y-axis. The axis of the egg is there. And everything else stays the same. So now you have 0 plus or minus C for where the focus is. Foci are. Okay. I think we beat that to death. All right. And you can go on from there. I don't think you need anything much more than that. I just want you to recognize what the formula looks like. Now, what if this looks a lot like what we had before, but with one major difference? What's that? Two major. Yes. Okay. Well, two. Okay. One plus or minus here. Second, this is a minus. Okay. What might we be dealing with here? No, not quite. It's hyperbole. Okay? When it's a sum, and you have two foci, it's an ellipse. If the foci are the same, it's a circle. If it's a difference, you're dealing with an ellipse. Okay? I mean, with a hyperbola. Okay? And here's the formula, or the theorem 2 that states that. They got right to it this time with a lot less rigmarole to go through. Hyperbola in standard position. Now, what does that mean? The center is at the origin. And guess what? The center is not part of either branch of the hyperbola at all. Generally, never. In fact, I don't think it ever would be. Okay. Now your A. We'll get to that. A greater than 0, B greater than 0. We set C is equal to this. What's the difference here? What was our C before? A square root of A squared minus C squared. Now it's a plus there. The hyperbola, the some point from focus 1 minus some point, the same point from focus 2 is going to be either plus or minus 2A, A being the greater of those two numbers, and with foci C0 and minus C0. Okay. Now this is going to be a hyperbole that its axis is the x-axis. Okay. The one that's positive, the one in front, that's going to be whose axis it is. Okay. Because guess what? When x is equal to A, y is equal to 0, and you have 1, right? 1 squared, okay. Can y ever equal B?
Well, yeah, it can't because it's B squared.
Okay. No, but it's a minus
yes,
a positive number. Yeah, I don't believe that's possible. That's the key. So what's the difference? Ellipse, a plus here, hyperbola, a minus here. Okay? Circle, they collapse on 1. Okay? And the A and B are the same. Okay. Now, this seems totally out of order. This is totally out of order. Okay, this was your ellipse that the y is the major axis. The foci are on that, and then this is the translation. They didn't show on the other way, but that's all it is. Okay. Notice your larger value, your major axis is under the y, so that's y, that's there. Your minor is the x. Okay? So this intersects at plus 5 minus 5. Happens to have the both sides 0, 4, 0 minus, or yeah, 0 minus 4. Because 3 squared plus 4 squared is 5 squared. Now, what have we done here? We just translated. So the shape, the size, everything else is the same as just translated. So that's a x minus 6 squared. It went from 0 to 6 on x. Y minus 7, it went from 0 up to 7. So that's all you've done to translate. We're not going to do many of those, but if you ever ran into them, that's what it is. But the form, looking at that, plus equal 1, got to be in the limit. Let's see if we're square. Okay. So that was out of order on the slides. Now we have our hyperbola. And again, this is along the x-axis. Yuck. Okay. This axis is the x-axis. Focal axis is the x-axis. Here are the two foci. And some point here, the distance here, distance here minus the distance there is what your constant now. But you could have said distance here minus distance there is your constant. I mean, it doesn't matter which way you go. But that's hyperbola with. You still talk about a conjugate axis, but guess what? It never crosses the conjugate axis. There's your main axis, and that's what a hyperbola looks like. Now, of course, if you had it this way, then your this would be a y over b squared minus x over a squared, whatever they would be that you want to call it. Whichever one is the positive, that's the one that axis it goes over. Okay. I guess this is just showing the dimensions. Remember, it's the variable that's positive. This would be x squared over a squared plus y squared over minus y squared over b squared. The b may be greater than the a. No problem with that. That determines it for an ellipse. It doesn't determine it. It's whoever comes first is positive. That determines the major axis minor. So the conjugate axis may actually have a value who is greater than the on the main axis. Okay? That's not an issue here with a hyperbola. They could even be the same because it's got a minus on there. It can't reduce into a circle because. All right. I think we beat that to death. Now, next shape. All right. This is your parabola. Basically, your parabola says that your distance from any point to your focus is equal to, and that's supposed to be a P prime times D, where D is called a directress. Okay, rather strange word. And let's just go to a picture. I'm sorry they got these pictures so out of order here. That was an example. Which one's that? Example 3. Okay. All right. Here now is our parabola example. All right. There's any old point P would be on that curve. Okay. The directrix D is y is equal to some. Now, if your axis is the y-axis, then y equal to some number. not inside the curve. It has to be outside the curve. This happens to be minus c here. Parabola with focus, 0c, directress, y is equal to minus c. So the distance from the focus to this point is the closest distance from the point, the perpendicular distance from that to the directrix. That line and this line are the same length. Further up here you go, the further up there you go. So basically, that's it. All right. Now, you might say, what's the point of something like this? And here, in a nutshell, is the point of something like this. Specifically in optics, but in many other things, have you ever used a parabolic anything? Except,
I mean, like I said, it makes me think of headlights.
yes, your headlights of your car, you know that metallic shape behind, that's a parabolic mirror, okay? Flashlights, parabolic mirrors. Anything like that are parabolic mirrors. You put the light bulb, and of course it's not a point source, it's something else. But put it right on the focus, then when you light that leaves this and goes down here, comes out parallel to the thing. Always, everywhere, it comes out parallel. So that's why your headlamps and your flashlights basically give you a beam of light. Okay? How about on the receiving end of that? Any of you have a dish? Those are parabolic mirrors. You put they're aimed toward the geocentric satellite, whatever company you have, wherever that is. They're aimed there. The rays coming in close to parallel, they're going to reflect off the surface and go right to the focus. And guess what they put on the focus? The receiver. And that's where all of them come, and that's where the signal comes in, added to that, so that's why a satellite way, way away, the dish is capturing all those, focusing them on the focus, okay? And that's where you put the little receiver that sits out there, and that goes into the house. That's your signal, okay? So yeah, you use these way more than you ever realize, okay? And before they gave us a definition here, they gave us a rather complicated example. There it is. I won't even spend time. That's a specific problem. Here is the theorem that tells you everything you need to know about a parabola. I've got to sneeze, so hold on. Trying to be nice to the people listening at home that was kind of far from the microphone as I could. Okay. A parabola in standard position, and standard position will again be the focus at 0c, directress y is equal to minus c, so the parabola is going through the origin because c and minus c origin is directly between that. This is what it's going to look. The equation will be y is equal to 1 over 4c x squared. Okay? Of course, c can't be 0, okay? Because your focus can't be 0. The directress would be minus 0. That's the same place. And, that would just be the origin. That's all you'd have. And it wouldn't fit the formula anyway. Okay. So the vertex is located at the origin. The parabola opens upward if c is positive, opens downward if it's negative. Now, reverse the things, and now you can have a parabola over here, a parabola over there. But we're going to deal with it like this. So what does it look like here? Well, one representation, the key thing is y is to the first power, x to the second power. That's what gives away a parabola. One variable is to the first power, the other to the second. Now, is there any way to make this equal to 1? Everything else is equal to 1. Right off the top, I can't think of a way to do it. Sorry. Yuck. Okay. I think that's all we have to do with that. Now, here's just another little blurb. I don't think this is all that important for us now. For ellipses and hyperbolas, let's see what that should be, hyperbole, in standard position, remember what your C was? That was for an ellipse. That's your square root of a squared minus b squared. That's what C was. This was the major axis. For an ellipse, for a hyperbola, c squared was the square root of a squared plus b squared. Okay? So, for an ellipse, c has to be less than a, right? So therefore, this ratio has to be less than 1. But it has to be between 0 and 1. Both of these are positive numbers, so it's between 0 and 1. It could conceivably be 0. Never equal to 1, because b always is not 0. Okay? For hyperbola, though, the c was greater than a, so this thing is always greater than 1. This is called the eccentricity. The e is called the eccentricity. And for an ellipse, it's less than 1. For a hyperbola, greater than 1. Okay. Let's go back to hyperbola. I failed to mention this to you. I think I did. Wrong picture. I should have pointed this out. I think I just sort of flew by this too fast here. This was our C, just like before. Notice A is less than C. I would have thought C had to be less than C2, but I swear I don't see that happening here. So I was going to, but the C over A is greater than 1, and in hyperbola, in the ellipse, C over A is less than 1. Between 0 and 1. Okay. All right. So, kind of a summary kind of slide here. Pictorially, anyway. Can we get them all on? Barely. Okay. Oh, and for a parabola, the eccentricity is 1. Okay? Ellipses between 0 and 1, parabola equal to 1, hyperbola is greater than 1. I thought of it that way. But here's what we have. The ellipse flattens as E approaches 1. And of course, yeah, okay, got it. They don't tell you what it would be for a circle, do they? Yeah, that's what I was thinking. It seems like it would be 0, and then it's flattening until it gets to, as it approaches 1. Okay? At 1, flat line. Okay? Now, for your hyperbola, though, but you see, remember, the eccentricity, I don't think could equal 1, equal 0, or it would be a ellipse anymore. Okay. For as E goes to infinity, so if E were equal to 1, you'd just be along the x-axis, then greater than 1, they branch out steeper and steeper until E equal infinity would be the approaching y, okay, the y-axis. Okay. Interesting way of looking at eccentricity. We're really not going to play with that very much. All right. What does this look like? Well, I don't know if it looks like much of anything. I thought at first it seemed to be like your parabola, your first definition of a parabola. What's that? Right. The thing is, yeah, that's exactly it. They put the constant in there of E, which is the eccentricity. That's the unified theorem, okay, that gets them all pretty much the same. All right. Here's another way of looking at, probably doing more here than we need, because I don't know if we'll ever use eccentricity in this course. You might use it somewhere, but not here. The ellipse consisting of point P such that P F is equal to PD, P prime D, and that's the direction. What's that? Oh, that's just the tail of the D. You're right. I was wondering why they put a prime, because they don't have a 1 point. But you're right. That's the directions. Okay. Actually, in my book, the first time I saw it, it was even worse than it looks like here. I think the type was wrong. That's just giving sort of a unified approach to it. I don't think it's all that useful to you here. Let's see. This is doing the same thing for the hyperbola. Okay. Again, I don't think we'll be using that. So here's the focus directrix definition, which is basically what they have been leading toward in all those last few slides. It's just a different way of doing it. What you have to remember this in that. And they don't do it for the parabola. But basically the parabola is y over, you can say y over b is equal to x over a squared. You don't have to do it that way, but think of it that way. So there's a reason I'm going over that now. Sort of hang on to this, file it back somewhere in a retrievable place, and we will get there. Now, what in the world is this slide supposed to show? It doesn't seem like it's showing me much at all.
Distance from the focus to the directrix.
Okay, but with no shape there. So I guess that's what is common in all the unified field theorem. Okay. You just throw in your ellipse, or you throw in your, maybe that's what they're getting toward, is what happens if you have a off-centered. Okay. We don't need to know that one either. Goodness gracious. Goes on and on. Polar equation for a conic section. I don't think we need this one either. If you ever do, there it is. Okay. Remember, E is eccentricity. Go back and do that. And here's the examples that usually they do early on. I did them there. Parabolic mirror. That's exactly what that is. This is a radio telescope. Make it a little smaller, and that's your disc outside for your TV. Whatever. Okay. But it's a parabolic shape. Okay. Is this anything better? I don't know. Seems like they're stringing this stuff out like crazy. No, this is just, I think this is just a review. No, it isn't. This is doing something about tangent lines, and yeah, I guess this is reflective. Okay. All right. I don't know if you realized I didn't, even though I've been in this once, I don't guess I ever dawned on me. It's ellipsoid dome, National Statuary in the U.S. Capitol Building, creates a whisper chamber. Yes, I was there for that, but I didn't know it was because it was ellipsoid. You know what they mean by that? There is one place somewhere in here, probably several, maybe along a curve there, and you can be whispering top secret to somebody, and everybody else throughout the whole place can hear you. Because that's what they call a whisper zone. You happen to be at a focus of that ellipse, and if you're saying something, it's going to reflect everywhere. So don't want to be whispering there, okay? Certainly not yelling there. Legend has it that John Quincy Adams would locate at one focus in order to eavesdrop on conversations taking place at the other focus. Clever guy, huh? Okay, now, what if you see an equation that looks like this? That doesn't look like any of our earlier ones. What do you make of this? What's that? Okay, here's what you do. Kind of. Get this one and this one, and maybe part of that F together. Not quite fair. This one and that one and part of that F together, and then here, what this has, you have, these indicate you have translations off the origin when you have these. Okay, this one means you have rotation. When you have a cross term here, you have ellipse has been rotated. How do I know it's an ellipse? Plus sign between the square terms. It's got to be an ellipse. Okay, and what this does is indicate you've got translation, and this means you've got rotation. Okay. Don't let the equal zero bother you, because if you gathered everything together and recombined them the way they needed to be, you would wind up having a constant out there at the end. So if you didn't, you could just subtract it. All right. And this is an illustration of exactly what I was talking about. Notice, find your square terms. There's a plus in between. So therefore, this is an ellipse. Okay? Since you have a minus here and a minus there, basically that's going to be an x minus something squared, the y minus something squared. Well, that means you translate it this way. Positive on x, positive on y, we call it the number. That's what that's doing. And since you have the cross term here, you have rotation. Okay? And equal 38 is just a ramification of what you got. Okay. We're not doing anything with that, but that's just what happens when that's the case. If you see them that are fairly complicated like this. Now, how about this one? Notice you have, again, plus sign in between. It has to be an ellipse. You have a linear term here, a linear term here. Your linear term in x is a plus here, meaning if you solve for x, ultimately, that would be x equal minus something. So that's moved you over here. The y is a minus, so that's the vertical translation upward. And you don't have a cross term, so there's no rotation in it at all. So this is merely a translation in both x and y. Okay. All I can think of saying about that. We're not going to really use those too much, but there will be one place that will show up later but that's the only place they do it. They show it and then they never come back to it really again. I don't think I want to belabor this one too much, but this deals with the rotation part. So don't sweat this much. We're not going to do anything with that I can think of now. You might in engineering, when you're dealing with off-axis stresses and things like this, you'll probably have these out your ears, but you'll go through whatever you need to get them. What's that? Yes, exactly. All right. Again, this is if you have a 45. A lot more. Okay. I finally here's your. This indicates you've got rotations. If you have the cross from X times Y, that means you've got to have a rotation. They'll give you enough in the other one to show that. These are both centered at the origin still, so therefore you wouldn't have a linear term in it. You would have just the square terms and a cross term. Okay. In fact, that's your hyperbola right there, 2xy equals 1. It's a pretty simple one. Okay. Now, this is not the directrix. This is a good old thing we've had long time passing. Anyone remember what you called that? Say again? Yes, it is. And what did you call that when we were using the quadratic formula? What did you call that thing? It was what was inside the radical. That was the discriminant. If b squared minus 4ac inside the square root was positive, then you have a real numbers. If it was negative, you had complex root. If that was a perfect square, you had rational roots. If it wasn't a perfect square, then you had irrational roots. Okay, so same type thing here. They still call it a discriminant. Okay, it's just different definition for it. Let's see. They ought to give this formula. Okay. Basically, I think they did earlier. I just sort of zoomed through it too quickly. Let's see if I can find it. Yeah, this one right here. That's your A, that's your B, and that's your C. Doesn't matter what the D's, E's, and F's are. That gives you your discriminant. And that tells you then, using that, then you get to this. Okay. Again, we're not using it, so don't get hung up about it. Okay. That finishes 11.5. That's all we're going to do in 11, because that's all there is in 11. You're not responsible for any of those. But let me go back and say this, reiterate this. Your test will cover 11.1, 11.2. Don't even think I'm going to test you on conic sections. We didn't do enough exercises there. But hang on to what you learned there, or what we went over there. And we're going to go on and start chapter 12, and your test will cover 11.1, 11.2, and then what I point out to you in 12. It's going to be most of 12, but anyway, let's move on to chapter 12. All right. And again, this is stuff that should have been covered, probably not in this detail, in Cal 2, okay? Did you have this in Cal 2? Okay. Any of you have Cal 2 elsewhere? Okay. It generally was. It should have been anyway. And this is vector geometry, which should have been there too. You know, we're not going to do all this. The first of this is amazingly simple, so we should go through this pretty quickly. Here we go again. I click on it and it sits there and blinks. And that's all it's doing. Okay.
Is it open on the bottom already?
Okay. If I go down here, that's what I got. Okay.
Oh, okay.
Yeah. But it quit it from blinking, and that's what I did last time. So now double click again. And now it goes back to quivering again, like it's nervous or something. I guess Cameron walked in the room and it got nervous. Okay. I swear, I'm sorry. What's that?
Exit out and come back in. Exit out.
Yeah. Let me try one more because it seemed like last time. Ha! This time it is because I saw the little circles show up. I think it is anyway. It quit quivering. Nope, back to quivering. Okay, exit out up here. Let's see. Let me back. Oh, I think I did this last time. I backed up. Hey, there it is. All right. I don't know what its problem is. All right. This isn't the same picture you have in your book.
I know what the problem is.
What is
You
it?
have to hit open. You're in PowerPoint already, and you're selecting the new file.
Yeah.
And it's just putting a check mark by it. You have to select it and then go down to the bottom right hand corner and hit open.
Okay. I haven't had to do that before, but I'm not saying you're wrong. It probably just...
You probably don't switch between PowerPoints a lot during class and stuff.
What's that?
You probably don't switch between PowerPoints a lot during your class.
No, I generally will finish one. I mean, not often, but I did. But it never had given me that problem before. But yeah, we'll try that next time if you can remember the sequence you're talking about. Good. Okay. This is the figure you have in your book, but it, I think, does the job pretty well, unless you have an older edition. You have ferrofluids containing suspended magnetic nanoparticles. It's a pretty interesting looking picture itself. This is a lot more macro thing. This is the recently completed Baling River Bridge in China's Guizhou province, 2.25 kilometers long. I'm trying to think, is that more than or less than a mile? It's awfully close to it. And soaring 400 meters above the Baling River, I guess is how you say that. The tension in the cables and forces on its towers are described using vectors. Okay? So basically, that's what we're doing, vector geometry. However you do it, whatever the thing you've got, you express that in vectors. What's this? I think it would be. I was trying to remember that exactly, but I don't, so I believe it is. Now, I think this is gross review for y'all, right? Y'all know what vectors are, right? Huh?
Victor knows.
Yes, Victor is a vector person, right? Okay. All right. He loves that. I don't know why, but he loves it. Okay. All right. A vector basically is a directed line segment. That's this one definition for it. What do we mean by directed line segment? All three of those are important.
It starts at a point and goes in a direction or to another point.
Okay.
And so it's
Okay, a line means the shortest point between two, and yes, directed means one's the initial and one's the final, so it's directed, it's got a direction. Line, straight, segment, terminal. Okay, a line is infinite in both directions, a ray is infinite in one direction, a line segment is terminal in both directions, but this is a directed line segment, so straight line pointing from one point to the second point. This is point 22 is the initial point, Q75 is the final point. So it's written as vector PQ, okay? Always when you write them like this, the initial point's first, even if the final point was over here, you still write PQ, or PQ, or PQ. If that's the initial point, that's written underneath this part, and the arrow is over the terminal point, okay? Now, all right. They also refer to this as initial point or the they call it the tail of the vector, and this being the head of the vector. I usually don't use those terminologies, therefore I wanted to make sure I said it right. The tail is the base point, and the head is the terminal point. And somehow to me they seem backwards. I use initial and terminal. Okay. Now this is any old vector like this. If you put this vector, whose initial point is at the origin, then this is called standard position, or they're just calling it position vector. And then it would be OR, okay, or OQ, or OP, but O is all the initial point if it's at the origin. I call it standard position, they're just calling it position vector, okay? Now, this vector is the same as any vector that has the same what? Two quantities. Same what?
Slope.
Same slope, which other word for that is direction, and
Same distance or scalar.
yes, length, or usually called length, or magnitude. The magnitude and the direction are identical. Okay, that's the opposite. So it has to be exactly the same magnitude and direction, length and slope. Yeah. Okay. So obviously these two vectors are not the same vectors. They could have the same length. I don't think so. Let me see. Yeah, they do have the same length, but they don't have the same direction. Okay? So I thought they looked like they had the same length, the scales are the same, but they don't have the same direction. So they're not the same vectors. Okay. Could you give me the same vector as this one in standard position?
0, 0,
5, 3, exactly, okay? And you're hitting right on the thing. And that's why I said they do have the same length, because 3 squared plus 5 squared is the same as 5 squared plus 3 squared. But we'll get there later. Okay. Here's saying, I think, a lot of what I was just saying. All right. These are all vectors. Here's vector V, the one we're starting with. These vectors are called parallel to vector V. Actually, I call that one parallel and this one anti-parallel, but they're both parallel to V. Okay? Parallel meaning in the same direction. Anti-parallel is in exactly the opposite direction. Okay? Now, when W is an exact translation of V, then we say these two are equivalent vectors. And we usually shorten that and call them equal. Okay? But technically equivalent. Okay. Let me make sure I'm hitting all the points here that they're saying. Their slideshow is a bit on the weak side. Okay, I've already said they're equivalent. Okay. Now, wish they didn't have all the words here. All the vectors in this are equivalent to A. Why? To V. In A. Or in the same direction, same magnitude, exactly. How about V here? Green vector is parallel, not the same magnitude. I'm not even sure blue is,
That
might be the same magnitude, but definitely different direction. So they're not equivalent, okay? How about V and V0? They look like they're equivalent, with V0 being the, yeah, it's called the position vector for V, or the standard position of V. It's an equivalent vector whose origin is at whose initial point is the origin. Is a unique vector based at the origin and equivalent to V. Okay. Now, a lot of times V0 will stand for something else later, especially in physics, but for what we're doing now, that's what the definition is. All right, now, here is a way to refer to vectors. Hands down superior to any other way whatsoever. Components of a vector. The components of the vector V, if you remember that first one that we had that went from 2, 2 to 5, 3, no, 7, whatever that one was, okay? If you remember that one, what you wound up giving me were the components of the vector, okay? If P, the initial point, is A1, B1, Q, the terminal point, is A2, B2, then the components of this vector are A2 minus A1, comma, B2 minus B1. The A is the, I'm going to call it now the horizontal component of that vector, A2 minus A1, the X component. I don't like calling it X, I'd rather call it horizontal component. And the B, or the vertical component, they're calling the Y component, is B2 minus B1. Okay? The pair of the components is denoted by, and notice the difference here and this. Points are enclosed by parentheses. These are coordinates of a point. These are components of a vector. Those brackets are slightly angled. I call them angle brackets. In fact, when I draw them, I usually try to put more of an angle in there so you don't confuse them with the parentheses, okay? Because sometimes when my eyes are tired, I have trouble telling the difference, you know, especially small print. Whether that, is that a vector or is that a point? A point has coordinates, a vector has components. Those words are close enough together. They can potentially be confusing. Okay. Now, and if that wasn't enough, okay, here's a vector V, okay, initial point P, final point Q, that would be the vector PQ, okay. Now, its components are AB. The coordinates of P, A1, B1, coordinates of Q, A2, B2. The components of the vector are AB, A being A2 minus B, A1, B being B2 minus B2, B2 minus B1, okay? Now, translate that vector, equivalent vector whose initial point is the origin, that gives us the vector, this book calls it V0, okay? Now, P0, which is the, and see, to me this is so confusing. Why wouldn't they call that Q0, okay? But they're calling it P0. It corresponds to the Q up here, not to the P up here, so don't let that confuse you. I just did, didn't I? This has coordinates AB, the point P0 has coordinates AB, but that vector V0 has components angle bracket AB, close angle bracket. The vectors V and V0 both have the same components, AB. They're both vectors, so you put them in angle brackets. But when you write the vector in standard position, they call it as the position vector, V0, then its terminal point will have coordinates AB, the vector will have components AB. Make sense? Again, probably beating horses that you know so well. Okay. Now, we talked about magnitude. What's that? Okay, yeah. You got it. We talked about magnitude. Here's the definition for magnitude. Okay? Now, does that symbology remind you of anything? What does it kind of look like? Absolute value. It's a double bar. Absolute value, what goes in there is an expression that represents a number. What goes in between the double bars is a vector, okay? And what that's giving you is the magnitude of the vector. Can also be written this way, double bars around vector PQ, where P is the initial point, Q is the terminal point. But here's the definition for it. Whichever way you describe it, it has a unique set of components, and the magnitude of that vector is the square root of the first component squared plus the second component squared. Okay. Does that depend on which quadrant that vector might be? No, not at all. Because whether A is positive or negative, or B is positive or negative, when you square them, they're going to be positive. You add those two positive numbers, they're going to be positive. Then you take the principal square root of that, it's going to be positive. That's how it's like an absolute value in my mind. Never negative. Don't ever give me a magnitude of the vector being negative. Can't happen, okay? It's a positive number always. So in that sense, it's kind of like an absolute value. Okay. Oh, yeah. All right. We assume all vectors are based at the origin unless otherwise stated. Okay? In other words, when we're talking about any old vector, we're going to picture that vector, treat that vector as if it's a position vector, standard position, or whatever, based at the origin. Okay? Why did they put that statement there?
No, it's not even in the chapter.
I don't see it anywhere here, but it. Okay.
Oh, it's in the old book. Okay.
Is that right? Okay. I thought it must be, otherwise, because this is the old slide set. Now, I keep thinking, I think we're going to get there. We have not gotten there yet. Before we go any further, let's go back. Right after they had this, they introduced the concept of the zero vector. Now, tell me what a zero vector would be. A point, exactly. Okay? What would be its magnitude? It would have to be zero. Okay? How about its direction? It doesn't have one. So therefore, there's a real big part of me that thinks the zero vector is really not a vector, because a vector has to have magnitude and direction. But a zero vector is the only exception to that. It has no direction. And it has a zero magnitude, which I guess we could get by with that, but it doesn't have a direction. Okay.
You can say it has zero direction.
Okay. No, I wouldn't say that, because that might indicate it's pointed at 0 degrees or 0 radians, and it's not. It has no direction. All right, I think I'm going to, I think I'll include this section on your test. Yeah, I'm sure I will. So let's do example 1. How are we doing on time? Are we? Oh, yeah. Huh?
153.
Okay, got 2 minutes. I think we can do example 1 in 2 minutes. if I can find the example. Ah, here it is, I think. Determine whether V1, P1, let's blow this up. Oops. Boom, I blew it up. Okay. Determine whether vector V1 here, P1, Q1, and vector V2 here, P2, Q2, are equivalent, where P1 is 3,7, Q1 is 6,5, P2 is negative 1,4, and Q2 is 2,1. Are those equivalent vectors? How would you determine that?
Take both magnitudes, divide them by each other.
Both magnitudes? That certainly would work. And you divide them by each other, what would you have to get?
I mean, if they're equivalent, you should one.
That would be 1, exactly. There's actually a little bit easier way to do it. Determine the components of these vectors. What's the component of V1? Not that hard.
32.
3 what?
32.
Not quite. 3 negative 2. Okay, because 6 minus 7. Okay. What's the component of vector V2? 3 negative what? 3 negative 3. So guess what? Not equivalent vectors. Okay? Same x component of the magnitude. This has a y component negative 2. This has a y component negative 3. No, they're not. And the reason I say that's a little easier, how would you determine magnitude? You'd have to get the components first, basically. So why go all the way to magnitude when you can stop at that? But even magnitudes, ratio of magnitudes being 1 still wouldn't guarantee it. You can take the same vector and rotate it anywhere you want it to. Its magnitude is going to be the same, so they wouldn't be equivalent. Okay, it has a 0 magnitude but no direction. Yeah. And there's a difference between no and 0. I mean, it's a strange kind of concept. All right, we'll begin next time. I guess we are out of time now. And with example 2. Huh?
156.
150. Oh, okay. No extra charge for that extra minute. Okay. All right. Good deal. So we'll pick up with example 2 next time.